must be a prior knowledge, and you must have already been introduced to this either in your science classes or in math classes in earlier grades, but let's go through it. The topic is on significant figures and scientific notation. So let's understand why do we need to know this. Significant figures are mainly useful in scientific experiments when we are using measuring tools like, for example, meter scale, vernier calipers, screw gauge, where there's a least count, that is the minimum amount, the least accurate measurement that it can make, and the answer would have those many significant figures or those many decimal places to what accuracy level it can measure, and that is the reason it is important to know the significant figures. The importance of significant digits, or the way we write it, is that it is estimated to the we accurately know to a certain digit and we estimate the next digit after that. For example, on a meter scale, the smallest measurement that you can accurately make is 1 millimeter or 0.1 centimeter, right? So for example, in this particular reading, you are able to clearly read 13.3. However, if the arrow was slightly on the right or left of 13.3, so you have to estimate the next digit after 3, correct? And that's your estimate, and those many number of significant digits will be present. For example, if it is exactly 13.3, then you will say 13.30. So you add one more digit to how much you can accurately measure. Here, for example, 12.8, it's not exactly at 12.8, it's between 12.8 and 12.9, and the closest estimate you can make for the next digit is 12.85. So that's how significant digits work, right? The same rule applies everywhere. For example, look at the graduated cylinder here. What can you read clearly, which is what it says with confidence, is the reading 56 milliliter. However, you estimate one more digit because it is exactly at 56, you say 56.0. That means you are able to read the first two digits clearly and you are estimating the next digit, correct? Same thing here, between 53 and 54, and therefore the digits, correct? So let's look at the rules that apply to how do we write significant digits in mathematics. All non-zero digits definitely will be considered significant. So each of the examples here is telling you the number of digits. You will be able to take a minute, and I'll take a pause here. So all we are doing is just counting the number of non-zero digits, right, in each of the numbers written. The second rule says that the zero in between non-zero digits, correct? So again, not very hard to see the examples and know. The third rule says all final zeros to the right of the decimal, correct, are significant. And so the digit in red is telling you till that point. So 32.0, that means you are able to read till that significant digits and therefore has 3 significant digits. If someone is reporting 19.000, that means there is a measuring instrument which was able to measure to that accuracy level, and the last digit of course is an estimate, and therefore will have 5 significant digits. So it is not that the 0 is written and you may exclude it. If in a measurement it is written so, it tells you about the accuracy level of the instrument, therefore it becomes important to write it to that number of significant digits. All zeros which act as a placeholder, and let me show you some examples here. For example, 0.0002 has only one significant digit. Now these are zeros which are placeholders. The reason why I say placeholders is, for example, if I change the unit, correct, to centimeters will become 0.02 meters. So what is the significant digit? Is it 2 or is it 0.02? So should I count the zeros or not? And that's where the placeholder comes into the rule, is that we don't count, and we will soon see how to get rid of this confusion. We will be introducing you to the scientific notation or the standard form of writing numbers, where you will no longer have this confusion whether it's significant or not. So in 6.02, if you see, 0 is in between two non-zero numbers, and therefore that is significant. 100.000, the zeros are after the decimal and therefore they are significant. However, in 150,000, the fourth example, all the remaining are placeholders, because if you had changed the unit, you would have got a different number, correct? And therefore, only 1 and 5 are the significant digits here. Similarly, in 800, only 8 is the significant digit. And of course, how many significant digits? Now, these are just examples for you to try. I will take a pause again for you to check if you have really understood what we are looking at. And the numbers are written in different formats. We will soon introduce you to the standard form. So in 0.0073, the zeros are placeholders and therefore only 7 and 3 are significant digits. However, in 100.020, the zeros after the decimal become significant. In 2500, the zeros are placeholders. However, in 670.0, all the zeros are significant. They have been placed because maybe there is an instrument which is able to measure to that accuracy level. Correct? In 0.0001, the zeros are placeholders. In 18.84, all are non-zero numbers, so therefore they are definitely significant. Correct? Now, how do we round off the digits? Correct? And this is again prior knowledge for you. The digit where we have to round off, you have to look at the digit after it, and if it is greater than 5, then you round off to the next number, the next digit, and if it is less than 5, then you do not change. For example, 43.82, we wanted to round it off till 3 significant digits, which means 8 is the last digit. After 8, I am looking at 2, which is less than 5, so I am not going to make any changes and I will round it off to 43.8. However, look at this example. It's 234.87. I wanted to round off to 4 significant digits, which means again 8 is the digit at which I am trying to round off. So the digit after 8 is greater than 7, so I'll round off 8 to the next possible digit, which is 234.9. And this is, you've been doing this from a very young age, so I don't think you really need to be told these rules, but it's just a recap of things. Again here, 78.657 needs to have 3 significant digits. After 6, you're looking at the 2 digits after that, and the digit following 6 is 5, and 5 is also followed by a non-zero number, therefore you will round it off, right? You can also think of it as 57. 57 is greater than 50, and therefore I would round off 6 to the next digit, so our rounding off will become to 78.7, right? And this is another example. Now, but look at here, 2.5350, I want 3 significant digits. I have the last 2 digits are 50, so 50 and above I round off to the next possible digit, therefore 2.54. If it was 2.5349, I would have left it to 2.53, because 49 is lesser than 50 and therefore the rounding would not happen to the next digit. Now you want to do 2.5250 and you want 3 significant digits, which means 2, the number to the right of the digit you want to follow, right? 50. You want the digit to be even and it already is, therefore you don't have to round it off. So 2.52 is what you will keep it as. These are some other examples. I'll take a pause again. But remember, the rule is greater than half or greater than half, you round off the previous. So if it's 5 or greater, then you round off the digits. 50 and greater, you round off the digits. 500 and greater, so depending on the number of digits that you have after the place that you are rounding off, you will look at whether it's greater than 5 or less. Now we are coming to scientific notation, and why is it important? So scientific notation is very important for looking at very large numbers or very small numbers. Majority of times, again, in scientific experiments, for example, hydrogen ion concentration, when you're looking at pH, are in 10 raised to powers of negative or positive numbers, depending on whether it's an acid or base. The sound intensity, light speed, all of these are very large numbers, or some of them are mass of an electron, very small number. So these are expressed in a particular format, and that's what we are looking at now. So let me first introduce you to the format and then tell you how to do it. So let's look at this. So the format is the first digit has to be a number between 1 and 10. Okay, and the rest of them have to be in powers of 10. For example, 3 is followed by 6 zeros in the first example. So I'm going to look at a digit which is between 1 and 10 here, which is 3. So I will isolate 3, and after 3, how many place values are there? There are 6 place values, and which are all zeros. So it's simply times 10 raised to 6. 6 to 6 again, followed by 7 zeros, correct? Now I am looking at a number between 1 and 10. So I will have to make it 6.26, because 62.6 or 626 are numbers greater than 10. The first digit has to be a number between 1 and 10. So 6.26. If I have to write the number as 6.26, how many place values have I moved to the left? 7 zeros, 6 and 2. So 9 place values have moved to the left, and that's the reason I have written it as times 10 raised to 9. Look at point 0005. The digit I need is a number between 1 and 10, so 5. But to get to 5, I had to move to the right. How many place values did I move to the right to get to 5? 3 zeros and 5. That means 4 place values to the right, and therefore times 10 raised to minus 4. So if I am moving the decimal to the right, obviously the powers of 10 are negative because I am dividing by powers of 10, right? And if I am moving to the left, then I am multiplying by powers of 10, and therefore the powers of 10 will be positive. Look at the next number. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 digits after the decimal place. Now I want a number between 1 and 10, so I will go to 8.45. Now to reach to 8, how many decimal places did I have to move to the right? 6 zeros and 8. So 7 places to the right, and therefore times 10 raised to minus 7. 2250. The number I need is between 1 and 10. So 2.25. How many place values did I move? I moved to the left. So 3 place values to the left. So times 10 to the power 3. Now that I have told you the rules, let's look at the other side of it. So 99.343, if I have to write it as a place value, again I need a number between 1 and 10, so I'll make it 9.9343, and I have moved 1 place to the left, so times 10 to the power 1. Now should I keep all the digits? Well, unless I have been told to round off to 3 significant figures, all the digits that are present, I will keep it as it is. Similarly, 4000.1, I need a digit between 1 and 10, so I'll make it 4.0001. I have moved 3 places to the left, so 10 to the power 3. I'll give you time to look at the next 3 examples. If I am moving the decimal to the right, the powers of 10 will be negative. If I am moving to the decimal to the left, powers of 10 are positive. And remember, the first digit is always a number between 1 and 10. I shouldn't be saying digit, it's a number because it could be a decimal number, it need not be one single digit. So that finishes our understanding of significant figures. Most of your answers in IB are to be given in 3 significant digits, and therefore it's important to understand how to round off, especially in chapters like probability, and also when you're finding out angles in trigonometry, then it becomes very, very important to know the correct rounding to the 3 significant figures, especially when you are also taking sine inverse, tan inverse on your calculator. Not rounding off before taking the sine inverse or tan inverse becomes important, because when you take the inverse after rounding off, your answers, your final answer is different. So these are some of the things that will be important when you are writing paper 2 especially, and that's why this prior knowledge becomes important for you.